Today we're going to find the zeros of polynomial functions. Some of our zeros will be real, some of them will be imaginary, so that's what's new for us. No matter what function I give you, you want your function to get to the point where you have a quadratic left and you can either factor it or use the quadratic formula. So for example, we all know how to solve this. This factors into 5x plus 7 and 3x plus 2. Once I have it factored, if I set each factor equal to 0 and solve for x, I get two solutions. You guys are really good at that. So if we can get our cubic function or our x to the fourth or x to the fifth function down to a quadratic function, then we can factor this and get more solutions, roots, x-intercepts, or zeros. If we're given a function, like we have in the second example, that is already factored for us, and we want to find all the zeros, then we just have to take the opposite of what we see in the parentheses. So if our factor is t minus 3, our zero is positive 3. If our factor is t minus 2, then our zero is positive 2. Now we have some imaginary zeros. If our factor is t minus 3i, our zero is positive 3i. And if our factor is t plus 3i, then negative 3i is our zero. So we have zeros at 3, 2, and plus or minus 3i. The zeros, remember, are the x-intercepts, the roots, the solutions of the problem. Now we're going to talk about some properties of polynomial functions that you should remember from Algebra 2. If you have a polynomial equation and the degree is n, then that means you should have, for a final answer, n roots. Also from Algebra 2, if a plus bi is an imaginary zero in your function, then a minus bi is also a zero. The reason why you always have two imaginary zeros is because they have to occur in conjugate pairs in order for our imaginary parts to cancel out. When you're looking at a function, you don't see an imaginary part in an original problem, but when you factor and find solutions, that's when you realize some of them could be imaginary. So if we're looking at this data, or looking at this next example, since it's an x cubed function and that's our highest power, it should have three solutions. If 3 plus I is a solution, then we know that 3 minus 5i is also a solution. Remember, you only change the sign of the imaginary part. I didn't realize all those would go in. All right, so the rational zero theorem tells us basically that we have to take p and divide it by q. When you read this theorem, it tells you that p is the factor of the constant term and q is the factor of the leading coefficient. For us, you'll hear me say a lot of times, instead of p over q, I'll actually describe. To find the possible rational zeros, you take the factors of the constant term and you divide them by the factors of the leading coefficient. So that's described in the definition as p divided by q. Now let's actually work through some of these problems. I am probably not going to have enough room to do both examples in one, so I'm going to cross this one out for now, and I'm just going to do example A, and then I'll delete my work and we'll go through example B. So I'm given this function, and the directions say use the rational zero theorem to find the possible rational zeros. So my possible rational zeros are going to come from taking the factors of the constant, which is 6, and dividing it by the factors of the leading coefficient, which in this case, I should put a number, is 2. So the factors of 6 are 1 and 6, or -1 and -6, 2 and 3, or -2 and -3. So we write that as plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. 1 times 1 is 6, but so is -1 times -6. And then the factors of 2 would be plus or minus 1 and plus or minus 2. You can't leave your possible rational zeros list like that. You have to write them out by taking any numerator on top and dividing it by what you have on the bottom. Okay, why is this not working? There we go. So I'm going to take 1 and divide it by 1, 2 and divide it by 1, 3 and divide it by 1, and 6 and divide it by 1. Then I'm going to have to take 1 and divide it by 2, 2 and divide it by 2, which is 1, and that's already in our list, 3 and divide it by 2, and 6 and divide it by 2, which is 3, but that's already in our list. So here's my list of possible rational zeros. There's a total of 2, 4, 6, 8, 10, 12 of them that I have to use for Part B. So in Part B it says use synthetic division to test the possible rational zeros and find an actual zero. Well, remember, an actual zero we can find by getting a remainder of 0 when we use synthetic division. So we're going to have to take all of these and just start trying synthetic division to figure out which one works. So let me clear my work right now. It is not erasing. There we go. And let's go back to synthetic division. So I'm going to have to try possible rational zeros. I can do this for a very long time. In order to make this process go a little bit faster, what I want you guys to do for your homework is take out your graphing calculator, and I want you to graph the function. Look to where you see x-intercepts and use one of those x-intercepts to put inside the box. So if you actually graph this function on your calculator, you would see that it crosses the x-axis at 3. So I'm going to use 3 in my synthetic division process. Bring down the 2, then we multiply, add, multiply, add, multiply, add. You must get 0 for a remainder. Because that tells you that 3 is a solution. If you tested 1 or -1 or 2 and -2 and did not get 0 for a solution, then you would not, or 0 for a remainder, then you would not have a solution. So now you take what's left. This started out an x cubed function, and now it's an x squared function, and you set it equal to 0, and you factor it. So 2x squared splits up 2x and 1x, and then this is going to be a -1 and a +2, and that gives you 2 more solutions, which would be 1/2 and -2, which then allows us to answer Part C, which are the zeros of the function. So we have zeros at 1/2, -2, And then don't forget the one you put in the box because you're trying to find the zeros of the cubic function, which would be 3. Okay, let's do this one more time. And I need to go back to that screen because now we have to do part B. So in part B, let me mark out A this time. When we're looking at B, we start out by finding our possible rational zeros. Our possible rational zeros will be formed from the factors of the constant term. Well, when you look at this, you really don't have a constant term until you factor out an x. So if you factor out an x, you're left with x to the 4th minus x cubed minus 3x squared plus 5x minus 2. Now if you look here, inside, sorry guys, my stylus isn't working, the parentheses, we have a constant term. So we're going to take the factors of 2 and we're going to divide them by the factors of our leading coefficient, which is 1. So the factors of 2 are plus or minus 1 and plus or minus 2, and the factors of 1 are just plus or minus 1. So when we list the possible rational zeros, we would have 1 divided by 1 and 2 divided by 1. So there's a lot fewer possible rational zeros that we have to test in this problem. But again, use your graphing calculator and pick the one that will cross the x-axis so that you don't have to waste time on your homework guessing and testing. Your homework would take too long if you did that. So if I look at my x-intercepts, I know that one of them is 1. I'm going to use the coefficients of the x to the 4th function. I'm not going to do anything right now with this x that I took out, but I will come back to that. So let's use these coefficients: 1, -1, -3, +5, and -2, and let's do synthetic division. Drop down the 1, multiply, add, multiply, add, multiply, add. Remembering the whole time that if we do this right, we must get 0 for a remainder. Now what that did for us is it took our x to the 4th function down to an x cubed. Remember, you want this to go down to a quadratic function so that you can factor or use the quadratic formula. So what we're going to have to do next is take the x cubed function, don't go back to the x 4th function, so take this answer here and these coefficients and do synthetic division again using a different 0. So if you look at your calculator, we also have an x-intercept at -2. So we're going to do synthetic division one more time, and we multiply, add, multiply, add, and again we have to get 0 for a remainder, so we're always checking that. Now that leaves us with a quadratic function that we can factor. So this factors into, I'm going to go over here now, x minus 1 and x minus 1. Those are the same factors, so we'd get the same 0, which also this 0 just happens to be the same as this 0 over here that we've already used. When we write our answer, we're going to say that we have zeros at 1, which we actually got that 0 3 times. You don't have to write it 3 times. We also had a 0 at -2. And then the last 0 that we have comes from this part of the function that I'm highlighting now. And then it looks like my highlighter undid what I had there. I had an x right there. So you know that you can take that x and set it equal to 0, and this is also an x-intercept. So we have zeros at 1, -2, and 0. All right, now let's look at the next set of directions because the directions are changing a little bit here. We want to find the nth degree polynomial function with real coefficients that satisfy the given condition. Well, first of all, the nth degree polynomial function, in your given information, I'm telling you what n is. So since n is 3, that means when we're done, we want an x cubed function. Now I'm also telling you some zeros. Once you see an imaginary 0, you've got to realize that another one comes with it. So -3i is also a 0. Let me erase my arrow right there a little bit. Maybe. So if I tell you +3i is a 0, then so is -3i. That's all we're going to worry about right now. We'll worry about this condition last. So you're going to take what I gave you as zeros, and you're going to write the factors. So kind of like we're working backwards. If 4 is a 0, then x minus 4 is a factor. If 3i is a 0, then x minus 3i is a factor, and x plus 3i has to be a factor. Now you're going to multiply these all out. So I would definitely multiply the imaginaries first, remembering that when I change the sign of the imaginary part, all my i's will cancel. So really I have to just take first times first and last times last. Because the -3ix in the middle and the +3ix will cancel out. So we don't have to worry about those. You do have to change the I squared to the -1. So this turns into, sorry I wrote x plus 4, I meant to have an x minus 4 here. This turns into x squared plus 9. So when I multiply this all out, I get x cubed minus 4x squared plus 9x minus 36. That's my answer if it satisfies this given condition. So you have to come back up here and you have to plug in 2 for all your x's. And you have to find out what f of 2 equals. If it equals -52, you're done with the problem. If it doesn't equal -52, you got to keep going. And in this case, when we work this out, we get our f of 2 to equal -26. But we know that it has to equal -52. So now you got to ask yourself, what do I need to do to this number? So what do I need to do to this number to get it to equal -52? Well, if you take -26 times -2, then that gives you -52. And this should be a +2, so our signs work out. So now whatever you just did to that number, you have to come back up here and do to this function. So if I'm going to multiply -26 by a +2 to equal -52, then I have to multiply my function by a +2. And there's my final answer. Now in the back of the book, they will actually multiply this out. So they'd have 2x cubed minus 8x squared plus 18x minus 72 as your final answer. I'm okay with you guys leaving it as 2 times the quantity of all that. So you can leave your answer like I have written right here. Okay, so now let me erase all that maybe. so that I can do the next example. Give myself a little bit of space here. On this next example, very similar to the last one, but our 0 changes a little bit. We still want to end up with an x cubed function. That's what that means. But now we know that 2 and, I don't know what this is, 2 and 4 plus I are zeros, and if 4 plus I is a 0, so is 4 minus I. So you're never going to be told both imaginary zeros, you have to recognize it. And then in the end, we have to satisfy this given condition. We'll worry about that when we're done. So we're going to start out with writing our function. We know that if 2 is a 0, then x minus 2 is a factor. If 4 plus I is a 0, then x minus that 0 is a factor. Notice that when you write 2, when you know 2 is your 0, you change the sign right here. You're going to have to change the sign of both the 4 and the I when you write this factor. So that's why I wrote it like that. So when you actually distribute that negative, it'll look like this. You have to change the sign of the 4 and the plus I in your factor. So same thing happens with 4 minus I. You would have to subtract the 4 and the minus I, which would change that to an x minus 4 plus I. Now you need to multiply all this out. This is the tricky part. You need to multiply all of this together first. Remember, when you change the sign of your i's, what that ultimately does is it cancels out all of your i's. You don't ever look at a function that has i's in the original problem. You get i's for solutions. So to make this a little simpler on ourselves with multiplying, these first two terms should always be the same. So if we multiply those two terms together, then realize that all of our I terms will cancel out. The only thing left to multiply together are these two i's. We don't want those to cancel because we remember that I squared equals -1. Okay, I don't know why this is all moving around on me, but it is. There. So now I'm going to change that I squared to a -1, which would make negative I squared a positive 1. I'm going to leave the x minus 2 on the outside, and I'm going to FOIL these. So I get x squared minus 8x plus 16, and then don't forget there's a plus 1 there. And that gives me x squared minus 8x plus 17. So the tricky step is right here with multiplying. Make sure you're trying those problems in your homework. So now right here you have to distribute. So I'm going to distribute my x to all the terms, and I get x cubed minus 8x squared plus 17x. Now I have to distribute my -2, which would give me -2x squared plus 16x minus 34. And I'm running out of room, so I'm going to go up here to the top. So my function, when I combine like terms, ends up being x cubed minus 10x squared plus 33x minus 34. So this is my final answer, maybe. We have to satisfy the given condition. So now you're going to have to go over here and find f of 1. I'm going to give myself some room here, so I got to erase some of this stuff. So if I find f of 1, then that would be 1 cubed minus 10 times 1 squared plus 33 times 1 minus 34. This really does work out sometimes in your homework, but it doesn't here. We're going to get f of 1 to equal negative 10, and we need it to equal positive 30. So now you got to ask yourself, what do I have to do to negative 10, and you're always multiplying, to get a positive 30? And that is multiply by negative 3. So whatever you do here, you have to go up here and multiply by. So your final answer for your function is negative 3 times the quantity x cubed minus 10x squared plus 33x minus 34. And that's it. Okay, the last two examples I would like for you to try on your own. I'm going to go ahead and go through them on your video, but I'd like for you to press pause and actually try them on your own first, and then come back and check them. Okay, with this example it says find all the zeros of the polynomial function or solve the given polynomial equation. Use the rational zero theorem and possibly the graph of the polynomial function shown by a graphing utility as an aid of obtaining your first zero. So since we can use a graphing utility, we're just going to substitute this into our graphing calculator, and we're going to go ahead and find an x-intercept, which we get to equal negative 5. So our x-intercept's negative 5. So now if I plug this into synthetic division, remember I should be getting a 0 for a remainder. And then that gives me a quadratic function because it started out x cubed that I can factor. And this factors into x plus 4 and x minus 1. So if x plus 4 is a factor, I have a 0 at negative 4. And if x minus 1 is a factor, I have a 0 at 1. So all we had to do on this one is find all the zeros. So I actually have to make sure that I include the negative 5 in my answer. Can't just leave it x equals negative 4 and x equals 1. On this last example, it's very similar to the first one. You are going to use your calculator to find one x-intercept. You're going to perform synthetic division, knowing you have to get 0 for a remainder. But then what happens here is that when you put in your x's and set this equal to 0, it doesn't factor. So if you get a quadratic that doesn't factor, you have to use the quadratic formula. So x equals negative b plus or minus the square root of b squared minus 4ac all over 2 times a. So I get 10 plus or minus the square root of negative 16 all over 2. The square root of negative 16 is 4i. So I get 10 plus or minus 4i all over 2. And then since both the 10 and the 4i are divisible by 2, I divide it. So 10 divided by 2 is 5, and 4i divided by 2 is 2i. So when I write my final answer, I have zeros at 5 plus 2i, 5 minus 2i, so those imaginary zeros, and negative 3. Don't forget that negative 3. We'll go over a couple of these when I get back next week, but we do have a test scheduled on Thursday. So Tuesday's a review day, test on Thursday. Come see me during STAR if needed, and have a good weekend.